All right, we're rolling. So let's start out with, are there any questions? Brooke?
Are you taking questions on the master set?
Sure.
Okay. For question 5, is at part B and part C, it's asking what is the electric potential at x is equal to -4 meters, and then what is it at 4 meters?
Right.
And I didn't really know where to start.
All right, so you have point charges here.
Right.
So these are, this is a one-dimensional problem. So it really doesn't matter where they are in terms of the explanation, but we have Q1 and then Q2. And I asked, what is the electric potential here and there at 4 and -4 meters? When you have point charges, that the electric potential from a point charge is just plugging into the formula KQ over R. So you would do it for what is the electric potential because of Q1 at that point, plus what is the electric potential from Q2 at that point, and just add them together.
Okay. So,
And then you would do the same over here.
okay, so dielectric constant time. So it would be the dielectric constant times.
No, not dielectric constant. That's Coulomb's constant.
Sorry, that's what I meant.
It's a K, not a kappa, clearly.
I switched that up in my head. So you do Coulomb's constant times Q1 over R plus Coulomb's constant times Q2 over R, and then you just add those together?
Yep. And if Q is a negative charge, then you're adding a negative number.
Okay, so it's R is going to be the distance from this negative thing.
Right, so R would be, for Q1, that would be R1 there, and that's R2 there.
Okay.
It's just a distance, it is a positive number, doesn't matter which direction it's in.
That would make that a lot more difficult.
Yeah.
Than it had to be. Okay, thank you.
Yep. And then D, even though you didn't ask about it, voltage is the same as the electric potential difference, and so you just subtract, I guess, from -4 to 4, you would take the value that you had in part C minus the value you had in part B.
Is that a similar process for question 4? Parts like C, D, and E felt very not confident about answering those electric potential difference and potential energy questions.
So when in number 4, we have a parallel plate capacitor, and let's see, I give you the charge and the size and the dimensions of the plate. I know that the magnitude of the electric field is sigma over epsilon, or epsilon sub naught. I can't remember if there's a dielectric in there or not. And that's the total electric field. And I know that the difference in the electric potential is basically E times D. And then you can just think through, well, I'm going from positive to negative plate, I'm losing potential. If I'm going from negative to positive plate, I'm gaining potential.
I have been really confused by that formula for some reason, and I don't know why. So the delta X is a distance between, say, the plate and a point charge or a point of some sort, right? Like, what all could that displacement be referring to?
All right, so it's the displacement. This formula right here makes the assume the electric field is constant with respect to position. Doesn't matter where you are, it's the same thing. So if we have our infinite plate approximation here, my electric field is constant in between. And so displacement is I'm going from this location to that location.
Yeah,
So I don't even have to have parallel plates. As long as my electric field is constant,
right.
I can come up with my electric, I have some region of space where my electric field is constant. I move 3 meters in the direction, same direction as the electric field. What's my change in potential? Well, it's E times 3, negative, because the electric field points in the direction of the lower potential.
And how would we know? Okay, no, that makes sense. Yeah.
So in the case of the parallel plate capacitor, the electric field goes from the positive to the negative plate.
Right.
The positive plate is the higher potential, the negative plate is the lower potential.
Yeah.
So when I go in the direction of the electric field, I'm losing
Negative.
potential.
Got it. Okay. Hmm. Could you say conceptually, just to clarify the difference between the electric field between the plates and then the total? I feel like I still am not, I get how to calculate it, but I'm not really getting why that's different. One has epsilon and one has epsilon sub naught.
Right. So when we figured out the electric field from a plate, we used Gauss's law, found the electric field from an infinite plate. So infinite plate, didn't matter how close we were to it, it looked the same. My electric field at this point right here, somewhere off the plate, magnitude is sigma over 2 epsilon sub naught. No matter what else is in space, that we have that. Now, if I have another charge right here, and I ask what's the electric field at this place, well, we have 2 electric fields that are combined. I have the electric field from this and the electric field from that at this point right here.
Right.
Similar to the parallel plate capacitor. I got a parallel plate capacitor and then I stick a dielectric in there. So some kappa. The plates create this electric field going across like that because of the charge. The dielectric creates an electric field going in the other direction. Because this electric field will polarize the molecules in there. And so I've got all these tiny little electric fields going back the other way. So the total electric field is the electric field from the plates plus the electric field that's created by the polarization in the dielectric.
Right.
So the total combines the two.
Yeah.
And that's made up of my electric field total is the electric field from the plates plus the electric field from the dielectric. So this is based purely upon the charges here. And then the dielectric changes that.
Okay. Thank you. Just to clarify, this sigma over 2 times epsilon sub naught, that's something we need to know cold, like that's always true. A point that's off.
If I've got a single plate, or infinite plane of charge, I should say,
Right.
then that is true.
Okay.
But with parallel plates, I got 2 of them, so
Right.
it's double that.
The 2 goes away,
Right, it will, yeah.
essentially. Okay.
In essence, 2 times a half is 1,
Yeah.
or so the math people tell me.
Oh. Makes sense.
But can we really trust the math people? I hope so. Still waiting for them to tell me how to divide by 0. Other questions?
Side one, I don't know if it had already been asked before, on the master set, question 5, you guys gone over that?
Yes.
Okay, I'll just watch the video.
question about F and G on question 4. I'm trying to get to that.
Very quickly, yes, it's good.
All right.
Answer his
So-
answers. We'll have to decipher if you want.
I got my plates here, and I put it to a positive plate, negative plate. My electron, it was an electron, right?
Yes.
Right. So the electron's gonna go that way. Now, if the electron were actually on the negative plate, then it would probably stay there, otherwise we've broken the capacitor by having it spark. So the wording should be the electron was placed near the negative plate, not on it, but it's going from near the negative plate to the positive plate, for the reasons outlined, I think, in problem 3. I know there's a change in potential here. If it starts at rest and starts moving off to the left, what's happening to the potential energy? Or what's happening to the kinetic energy?
Gaining kinetic energy is decreasing potential energy.
Okay, so that's an important thing to know there. I know that the change in potential energy is just equal to the charge times the change in the electric potential. Just as force is equal to the charge times the electric field that you put the charge in. So the change in the electric potential, I think, is either given or you're given enough information to find that out, or you answered that one already. The voltage from the positive plate to the negative plate. So part C, you've answered it. Except in this case, you're going the other direction, so instead of a loss, it's a gain. Charge of an electron is something good to know, but look on the first page of the test or quiz if you need to know it. And multiply it so you have the change in potential energy. I would expect it to be a negative number. And it should be, because if I'm going from negative to positive plate, my change in electric potential is positive, my charge is negative, and so therefore my change in potential energy is a negative number. I'm losing it, just as you said before. Because we're dealing with electric forces, energy is conserved. That means that my change in kinetic plus my change in potential better be 0. Because my energy should stay the same. And so, because the last part was, how fast is it going? Yeah. So my change in kinetic is equal to my negative change in potential, which is good because my change in, man, my language got sloppy there. The change in kinetic energy is equal to the negative change in potential energy, because there is a difference between potential and potential energy. The change in potential energy is negative for reasons outlined before, and so the negative of that is a positive. So change in kinetic energy is a positive number. Please don't end up with a negative under the radical and then just erase it because it's inconvenient. If you get a negative under the radical, the question is, either you've made a mistake or the problem is not possible. So ask yourself, if I put a charge there at rest and it goes to the positive plate, is it possible that it will have some speed when it hits the plate? I hope you can envision the fact that yes, it is possible. So a negative under the radical would mean that you've made a mistake. I guess you're having trouble seeing.
No, something popped up on your screen, but then it went away. So I was gonna see what it said, but it's gone now. I don't know if it was about the battery or.
Oh, looks like that's gotten unplugged.
That must have been it.
Is it recording?
Quick tilt for the stuff that I wrote off screen. All right. It starts at rest, so what's, well, change. What am I subtracting from what to find change?
Final minus initial.
Okay? So K final minus K initial is equal to whatever that is. What's my initial kinetic energy in this problem?
0, because it's at rest.
And here we go. What's the formula for kinetic energy?
1/2
F
mv
V
squared.
squared.
Not the enthusiasm I was hoping for. mass of the electron you can look up, solve for speed. Now potentially I gave you far more than you asked for, but, so.
No, that helps a lot.
Yes,
I was really
yes.
lost.
I tried using our like drift speed formula to find that, but it didn't work, cause like, that's more so concerned with like the mobile charge carriers, right?
Yeah, so the drift speed works when you have an electron traveling through a wire, not through open space.
Okay.
If there's a dielectric there, is there a dielectric there?
No, there's not.
Yeah. If there's a dielectric there, then don't expect the electron to really travel through it since it's an insulator.
Okay.
Should be a nice little twist question, but. Other questions?
Because you have emphasized this whole, now you know 600,000 ways to explain why, I assume we're going to need to be able to say at least one of those on our exam.
I don't know. I've definitely asked it in the past.
Yeah.
I've asked you to know all four. I've asked students to know all four. I've asked students to know at least one of them. I try not to write the test too far in advance so that I really don't know those answers
Okay,
too far in advance.
fair, but it's fair game anyway.
It is fair game, yes. In the absence of other questions?
Sure, you can. I feel there's just a little bit of confusion about that over here, Dr. Fox. Would you tell us what those four things are in fact referring to? Just for a refresher. Yeah.
You guys are talking about explaining why an electron would move towards hot, right?
Oh,
Yeah.
okay,
3D.
okay.
Yeah,
Basically.
we figured it out.
I just didn't know what you guys were referring to, but I knew
The
that.
last part of it.
But you're good now?
I'm good now.
All right.
It's essentially what all of question 3 is getting at.
Okay.
Which I did great. I had no idea what I was doing. I realized I didn't know anything, so we need to work on that.
We
I
just-
would like a refresher too.
Oh, you still want me to do it?
Yeah, could you, also,
Alright.
before you do
The-
that,
Okay.
sorry, I should have asked you this before you erased it. So for the speed of the electron, do you really need the context of the problem, or do you just need the mass of an electron?
You needed to know the change in potential energy.
Right, so
So-
if you know it's zero,
No,
or,
no, change in potential energy, as is written right there.
what was?
The change in potential energy is equal to the charge times the change in the electric potential.
Right,
And I know that the change in kinetic energy is equal to the negative change in potential energy.
oh, okay, so, wait. So once you find, so you just have to know that, so you have to find the change in potential energy first,
Right.
and then the inverse of that is your kinetic energy, and then with the kinetic energy formula, you solve for the speed.
Yes.
Cool, thank you.
Mhm.
You can erase it now if you want.
Also, total side note question, not about that. Is there any chance in this course that we will need to recall or use something from Physics 151 suddenly? Is that ever fair game, or is it like only the material we have covered in this class?
Well, I mean, kinetic energy is something from 151, so,
Right.
yeah, I mean, there's some things.
Right.
Occasionally, you run into the cake formulas,
Right.
and so that, I have asked that on, there have been 152 tests where you need to know how to use them.
Right.
It wasn't that you had to have them completely from memory, they should have been on the first page, or
Right.
somebody could ask and I could write them on the board.
Right. That's what I thought this question was getting at, but we hadn't run through a problem in class where we really had used it. You had brought it up at some point, that's really what spawned the question.
Yep. So it's fair game, but it rarely goes past, there's F equals ma, which I'm hoping everyone in here knows. The cake formulas, which I at least hope that if you saw them, you go, okay, that's right, the constant acceleration equations.
Right.
And kinetic energy.
That's fair.
Are the cake equations the kinematic formulas, is that what those are?
Yes,
I'm not, okay.
constant acceleration kinematic equations.
I've never heard them called out.
I'm the only one.
Okay.
So it's, most physics textbooks, it's those 4 equations they give you in chapter 2. Sometimes 5. All right, other equations or other questions before I do the why do charges move? All right, so why do charges move? Well, force, that's the simplest one. Don't overthink it.
Opposites attract.
There we go, force is done. Electric field. So the rest of them are come in 2 parts. One is establishing the creation of sort of the situation, and the other one is the reaction of a charged particle in that. So the first one is that the electric fields go away from positive and toward negative. And then a negative charge in an electric field travels opposite to the electric field. Positive charge in the electric field travels with the electric field. And then you can provide, change the wording around for context. But if the electric field goes to the right and I put a negative charge into it, it's going to go left. In the electric field explanation, you have no idea what's